morning, everyone. Can everyone hear me all right? Okay, I'm somewhat concerned I'm going to race through this too quickly, so I hope people will any sort of flagging will make me slow down. So just feel free to do something like this, and hopefully I won't be like, what do you want? And I'll just slow down. So I'm going to be talking about machine learning for essential iOS use cases. This is building on a talk I gave here last year, which was coinciding with the introduction of CoreML, right? So CoreML was released last year. Can I see a show of hands for people who have used it or have heard of it? Okay, and how about people who haven't? Okay. So here's the outline. I'll talk briefly about the motivation for CoreML. Why did Apple do this now? A quick CoreML overview for those who haven't seen it at all. It's very easy to work with and intuitive. And then use cases, right? Where are you likely to put this into your app? Where is everyone putting it into their app? Very common and really impressive use cases. And a little bit about what's likely to happen in the near future. So the bulk of this talk is going to be about the use cases. So in a way, that makes this a little bit of an awkward talk for an iOS conference because the iOS bit will sort of be compressed. And then mostly I'm interested in talking to you about how the models that you're putting into your apps work. And I come from a perspective of thinking the more you know, the better, right? So this is easy and great because what Apple has enabled you to do is just drop these into your apps. And yet, I want to be the downer and say, yeah, but you don't really want to use something if you have no idea how it works, right? And you don't want to be in the position of your colleague just saying like, oh, just use it, but not being able to understand what that colleague did before you put that in. And I think especially the pressure is on iOS engineers because you are the last engineers who touch the product before it gets to the end user, right? So when they start making those complaints or being unhappy, you're the one who's sort of first in the firing line as well. Okay, so motivation, just a personal story, and I'm sure we all have these. This is more for sort of like the really young folks in the room who might not even remember back to like 2012 because maybe you were still in high school or a college dorm room and this was not as memorable for you. But I remember I visited Japan in April 2012. And I think when people travel, everyone says, oh yeah, like everything's in English, it'll be fine. And usually that's true in most continents, right? But somehow, like I thought it would look like this when I got to Japan. There'd be a little bit of English, especially in like Tokyo, like there's probably millions of expats are passing through there all the time. But honestly, my experience was more like this. Like there was no English script anywhere. So that was my visit to Japan. I was very lucky that my husband reads Chinese and there's some overlap, so sometimes we could kind of cobble things together, but we were really lost. On the other hand, the people we visited, they came from Japan to New York City in 2017. This was their experience with the Google Translate app. They would be like, oh, like no Japanese, I don't know this word, let me just hold up my phone and like see what's going on here. Like let me just have my Japanese version of New York City when convenient, and it was just sort of mind-blowing. It's easy to forget, just like iOS itself has developed so quickly, AI, modern AI, and its success has really developed since 2012, and it's gone from basically nothing to feeling like it's almost everything, at least for someone like me who works with this stuff. Here's a very commonly shown graph from Google showing how they've been using deep learning in particular, which is one kind of machine learning. In 2012, it's basically zero, and they've had this sort of exponential growth where it's now in all of their products, or almost all of their products. And I think that's fair to say of a lot of large companies that have lots of data and lots of use cases where having your app be a little bit smart would be really useful, right? And so there was my Japan trip versus my friend's New York City trip, right? And that was part of why our experience was so different. A little bit also just about the social side of this stuff. The best tech right now is in industry, not academia, right? This stuff is very resource intensive. I think we're seeing like never before in any scientific discipline that academics are either leaving academia or they have very deeply entrenched cooperations with large technical companies. State of the art is often a trade secret. So many of the things that are amazing, that are powering your AI that you have in your home or on your phone or on the web, no, it's not even common knowledge how they work, how the very best works, or how well they work. May not even be reported. On the other hand, there certainly are some very good open source models. Those are out there to use in CoreML, for example, and you can also improve on them for CoreML. And there are things like contests that go a long way towards improving performance. So in a way, I think this will sound familiar to people who have been in the iOS ecosystem for a while, right? Things start working out of the box. You have lots of bells and whistles, but it's increasingly opaque. So that's sort of the backdrop of what's going on with the models that you are going to put in your phone. CoreML overview, just in a couple of minutes. For those of you who were here last year, you'll recognize these, so I'm really going to fly through them. What is CoreML? Well, first what you need to do is you need a model, right? You're going to put a model in your phone. How do you do that? Offline, not on the phone, right? Because training on your phone is still not happening quite yet. You're going to get a bunch of examples with labeled right answers. You're going to run them through whatever algorithm it is that you use to train your model, which can be a variety of things, to get as close to the right answer as possible, right? And all of that can actually be unpacked for hours and hundreds of pages, right? What does it mean to be close to the right answer? What kind of model? A model can be something that has one parameter. It can have millions of parameters. Both such types of models are in use in consumer-facing applications. And how you get your examples is actually also a really rich source of research, for example, because part of the reason we have AI growing the way it is because we have the web and social media and all this, and all of a sudden we have all these data sets that are often labeled also, right? Like suddenly we have all these Netflix reviews with human language plus numeric ratings. Oh, great, I have something that connects languages to numbers, right? Or if I want to model human language, suddenly I have Wikipedia, I have millions or billions of words just for free on the internet, right? So as some academic who couldn't put this data set together myself, I suddenly just have it for free. So that's sort of the data input. What CoreML really is doing is helping you with the inference, right, which is a part of actually using your model for something practical. You put in one example now that it's been trained, and it chugs through whatever it does, and it gives you a label, often with some sort of guesstimate, right? Like I think, for example, here, this is a rose with 95% confidence. And usually what you'll have, say, with this kind of classification task is you have a bunch of labels, and it will give you a probability for each of them, something like this. There is a whole universe of separate ecosystems of ways of building models, training models. The great thing is CoreML, even when it first came out last year, already sort of serviced all the main ones. So you could work with colleagues who've worked in a variety of languages or systems. They could come up with the model in their preferred computer language, computer environment. They could give it to you, and you could get them all into your app, which was really nice. That has continued to be the case. Apple has contributed more, and other organizations have also made more, so that the models you trained on a server somewhere can now more easily like click a button, and you're good. They go back into your phone. And once they're in your phone, they are just compiled into binary. You have this easy interface, just like I'm showing here, right? So you initialize and just pass in whatever the input is. So what does the stack actually look like? It's something like this. So it's all built on Accelerate and MPS. Then you have CoreML. You also may have worked with some specialized CoreML, right? There's Vision and NLP, precisely because these are two very common use cases, right? You want your phone to see like a human and talk to people like a human whenever possible. CoreML was really revolutionary because it brought machine learning very easily into a really commonly used device and enabled people, iOS engineers who might not have much background here, to nonetheless make their apps really, really smart, often maybe even without the help of an AI or machine learning researcher, because there are so many open source models you can download. So if you have some level of proficiency, you can actually get pretty far these days because there are these publicly available models around. Nice things about doing this on the device, right? I think it's fair to say CoreML is really one of the first cases of on-device AI rather than sending things over to the server, chug on the server, come back. Privacy, that's a huge one, right? So suddenly, instead of having to send all of this data about your users to your server, back and forth, you can just do everything on the phone. Wonderful, right? Then you don't need to store it. So to the extent that you don't want that private data, you don't want the liability for it, you no longer have it. Wonderful. You also get speed, right? There isn't this network latency component, right? It might be that your AI, whatever it is really, really fast, but nobody appreciates that because for some reason your server is really, really slow or network traffic is really, really bad. Also can be serverless, right? So you have something that is just useful, self-contained on its own, and again, then not worrying about network latency. You have an app that can work on the top of Mount Everest or down in a tunnel in Thailand or whatever, right, and still be smart. So these are all really nice things. On the other hand, you can't protect your IP, right? Your model, which can cost, if you're a big company, millions of dollars to develop, hundreds of AI researchers, paying lots of money to get your data set. In some cases, that can nonetheless, it just boils down to a large numeric matrix. And so in a way, you spend a lot of money developing these models, but you're actually very vulnerable because your end product can nonetheless be very easy to steal. So from that perspective, it's not so tempting to want to put your model on a device. So that's something to think about when you're thinking about when this is appropriate. It's also harder to detect and protect against attacks. So there's a new thing happening mainly in the last 3 years, especially with neural networks, right? These are the really hot, they seem to solve everything type of technology. People have figured out that sometimes they seem really smart, but if you tweak the inputs a little bit, you can suddenly make them do really dumb things, right? So you can take a self-driving car, and if you just manipulate a few pixels, or they even showed in real life, if you sort of hang something in a weird spot in a real physical environment, you can totally throw the car off, and you can get it to drive right into a tree. Or you can get an algorithm that labels birds to say that a penguin is really a flamingo, even though to a human, it still looks like a penguin. So there are ways that you can manipulate the outputs of these things. And then that's also worrying for people who say, well, if my model is easy to sort of find on the phone, it's not encrypted, that's going to facilitate that process. So that's worrying. Also harder to get feedback about how your model is doing in the wild. If this thing is just sort of released and chugs along, and you end up not sending anything back to your server, you actually don't know how it's doing other than maybe your App Store reviews, right? People might say, oh, this stylizer doesn't work at all, or this thing said it was a flamingo, but really it was a penguin. And you don't really want that kind of really slow feedback. And also then harder to know what real-world use cases your users are applying this for, right? You might have one idea for your app, and then actually if people are sending their inputs to your server, you can look at them, right? It does sort of go against their privacy, but at the same time, it allows you to find out what people are actually doing so you can tailor your product to them, right? So there's always going to be this tension between privacy and accuracy and performance. Okay, so then WWDC 2018 shows a lot of improvements for CoreML. CoreML 2 is all about performance improvements, which makes sense because I think right now, sort of the state of the technology is quite ripe on the server, but there's still the problem of how do you get this to work on a phone? And in particular, some of these models, like I mentioned, can have millions of parameters. How do you get that into an app in a way that people aren't going to mind, that isn't going to have people not downloading your app? Things like that. So Apple focused on size, inference speed, which is how quickly you can make the predictions, and customizability. And customizability is saying, oh, I don't want to just use sort of the pre-canned models that have been implemented. I want to write my own. So you may or may not have seen this talk, but one thing I noticed about these two CoreML talks is they wouldn't have made any sense to me at all if I didn't have some background about how these technologies work. And so that's another reason that I think if you are in an organization that is using this at all, even if you are sticking to sort of the front end and you have no desire to train models, you still want to know how they work. Because you think, oh, what's a layer? I don't really know what a layer is, right? And that can sort of throw you. And you want to be able to just listen to these talks and have them make sense. So that's where I'd say you definitely want to have some basic knowledge of how these things go. Okay. So particular use cases. The use cases that jump out at me that I think are really interesting and revolutionary, right? I mean, they're working so well now, they don't even feel that way, but you have to sort of project yourself back to 2012, and they really are, right? So one is optical character recognition, another is text-to-speech, speech recognition, object detection, and sentiment classification. So we're going to go through these and talk about how the underlying models for these things work. So optical character recognition. First thing I want to point out and keep an eye on as we go through this is if you can do optical character recognition well, there are other things that leads you to, or those things lead you to good optical character recognition. So one is image classification. Why does image classification relate to OCR? That's kind of weird. Well, not really, right? Usually when you do OCR, you're going to sort of take a picture or scan some document. It might be kind of slanted. It might be a newspaper, so there are some images as well as some text, and then also maybe some advertisements, so there are separate components of text. So actually, OCR is deeply connected to image classification. You want to be able to segment your images. You want to intelligently label different regions of the image you're trying to use for OCR. And in fact, this was a big part of why OCR was so difficult for so long. right? You think, even in the use case of only a couple of fonts, only one language, why is this so hard? Because actually it's really an image classification problem. Similarly, if you can get good at OCR, you can also get good at generating characters, that is at writing. I don't mean producing content, like producing something that makes sense, but you can tell your algorithm, oh, write an A, and write it in this style, or write it in that style, because the same techniques that are gonna help you take an A out of the wild in a variety of fonts and orientations can then be reversed to produce that. And then this is also being used in industry, so I've noticed, for example, there's a startup that has robotic hands writing handwritten thank you cards, right? That sort of thing. That is deeply connected to OCR. So OCR, why? Well, I don't really need to tell you why, but let's just think about it for a second. Lots of tasks that require people are really boring, right? And most of them just boil down to reading text in the world, right? Lots of things where we all wish we didn't really have to do it, it's not super compelling, and yet we still can't automate it. I think a great example is, for example, the USPS employee exam. A large section of it just boils down to OCR in a way, right? They'll show you an address, and they'll be like, quick, what's wrong with this? Or which of these addresses is wrong? Quick, quick, quick. And it's almost sort of like, how quickly can you visually process that image and identify the problem, right? Turn that image into text, find the typo, and go back. You really don't realize how much OCR you do until you do something like go visit Japan, where you can't read, and you realize that you can't even find a bathroom, you can't find food, you can't do anything, you're just sort of standing there. And that's been a limiting factor for all sorts of AI applications, right? You can't really have driverless cars until they can read the road signs. So just a reminder, OCR is fundamental to lots of other things we would like to do of having computers act like humans in the physical built world. Other examples, AI for medicine, for example, you want your robot doctor to be able to pick up your charts and just be able to read them. Okay, so broad strokes, why is this hard? We've already talked about this a little bit. It's already an image recognition problem or an image segmentation problem. That is already hard, but you also need to do more than that, right? You have to find where the text is. You have to figure out the orientation of the text. You can have font issues, right? Some fonts are sort of evenly spaced. Some are slanted. If you're trying to do handwriting, personally, I cannot read my own handwriting after I write it, and I know I'm not the only one in this room like that. But yet, I expect my computer to do it, right? And then we can add on language detection, for example. So there are all sorts of things going on here. So where do people begin to make progress on this problem? Well, one way you can look at this is from the MNIST database. Raise your hand if you've heard of or seen the MNIST database. I think anyone who's taken a machine learning class, right, has seen this thing. It's 60,000 training examples and 10,000 test examples. It's a great industry standard and has basically been beaten to death. Currently, at least from what I saw in a recent compilation, the error rate on this classification is down to 0.23%, right? So basically 1/5 of 1%. That, though, is very recent. About 10 years ago, people were getting down to only 0.63%. Now that's also, I mean, you can look at that and say that's really good, or you can look at that and say that's 3 times the current error rate. So it's either tremendous progress or not much progress. But what I would want to point out is that the linear classifier, let's see if I can use this. The linear classifier, which is the really simple one, is 6%. I mean, that's really terrible, clearly unacceptable, right? Like if you want to direct mail or check student grades or read medical charts with a 6% error rate, you can't really do it. With a 0.23% error rate, probably you can, right? Other than something that's truly life and death, I would say 0.23%. If you lose 1/5 of 1% of my mail, I'm probably okay with that. That's probably okay. I mean, I don't know if USPS would agree, but anyway. So these are the error rates currently for this problem. And I don't even know if anyone works on this problem anymore as far as increasing performance. You might still work on it to do simpler models or faster models, but sometimes problems are just sort of officially over. And I'm not sure that the human error rate is even as low as 0.23%, because people even get some of these wrong. And just, again, to remind you, that's the state we're at with neural networks, is they're doing better than people. Right? If you put them up against each other on tasks that we think of as fundamentally human, like reading a number, we're already not doing as well. So keep that in mind. So this was the sort of first task that people really turned their minds to as far as OCR. That was like a very controllable task. So how did we get from 6% to 0.63 to 0.56 to 0.23. Well, all of the methods up until recently were generally doing things like feature extraction, right? So they would do things like say, oh, let me pick this upper left-hand pixel. I'll give that a coefficient. This center pixel, I'm going to give that a coefficient, and so on. There's a couple of problems with this, right? Firstly, you have to have your grad students or your first-year engineers be really bored and like sort of think up things to try and then hand code them, or maybe write things out to code them. You write lots of for loops. You extract your features. It's not really compelling. You try them. Lots of them don't work. It's sort of really exhausting, not especially rewarding, and not super performant, right, when you think about all the time for humans that you need to use. What happened recently, though, is people use neural networks, and in particular, convolutional neural networks are used for image processing most successfully. So what is a convolutional neural network, which is a CNN? Well, the basic building block is up here. Let's say this is your input image, okay? This upper left-hand corner. You might say, I'm going to look at a size like this, a 3 by 3. So this is my original input. I'm going to filter it like this. So I've got 1. It's going to be element-wise multiplication. So upper left-hand corner with upper left-hand corner, middle left with middle left, and so on. And I'm going to sum these up. And then basically what I'm doing is I'm condensing my image, right? I am taking this here, multiplying it here. And so by summing, 3 by 3 is 9 elements. I'm going to get this number. And what you'll see is I have condensed this thing to a smaller image. That's not fundamental, but the idea is you are taking a region of your original input and expressing it in a different way. And you can tweak all of these things, like how big is your filter, what are the values of your filter, how many filters do you apply, how do you combine those filters with each other. We don't need to solve those problems, and in fact, often nobody does. You actually let the algorithm even figure out these things. How many filters should I use? What size should those filters be? What order should they be in, right? That wasn't originally the case, but that's at the point we're at now, where actually you just sort of tell it what general kind of architecture you want, and it sort of chugs through and gives you something that works pretty well. So you have these convolutional layers. So when Apple talks about layers, this is really what they're talking about, and this is where you can get something here that will help you with WWDC talks. A layer is really just sort of a matrix. A layer is a way of applying one matrix to another, right? So you have some sort of input matrix or input list, and you have a series of operations you're going to do. That is really all a layer is. So when you hear layer, you should really think like matrix multiplication. There's another kind of layer very commonly used in this sort of setup, and that's called a fully connected layer. I've got that pictured over here. This is even simpler to understand. A fully connected layer means you've got your input, you've got your output, and you're just going to connect every input to every output. And that's the output for that layer, not the output for that model, right? So you have every input to every output. This one almost sounds like when I was 10 and I thought, how would I solve every problem in the world? One way you could like sort of think about it as a 10-year-old is like, I would just have lots and lots of parameters, and I would tell the computer to figure it out. And if my model is complicated enough, it would work. And that's sort of how fully connected layers work. They work surprisingly well, although not as well as things, say, that are tailored, right? So what people have found is the sweet spot for things like OCR and image processing in general is some combination of first convolutions and then fully connected. And so here I'm showing you, for example, one very successful architecture, again, to give you also an idea of the complexity. We see we've got our input. It goes to convolution layers. So each of these is really the output of this applied to the original input. And then this output from one layer then becomes the input for the next layer, right? So you first have a convolution layer. You have something called a pooling layer I'm not going to go into. Then you have another convolution. So you take this output, you run it through another set of convolutions, and so on and so on. And so what ends up happening is you take your image, maybe it's 1024 by 1024, you condense it, condense it, condense it, and then at the end, you run it through something like a fully connected. You take what are called features extracted from these filters, you condense them, and you get whatever your answer is going to be. It could be a classification, it could be a numeric output. It's hard to think about. This is something, if you're really going to get into it, you want to work through by hand. But what's less difficult to think about is sort of the output from these filters. So these are the outputs just from like one layer of filtering a number 5. And what you can see here is sort of what things get picked out by different filters, because you have many filters, and when I say filter, I really mean layer. It's another way of talking about it. You have many different filters or layers, and they pick out different features, right? So this one seems to pick out sort of non-continuous points, right? And then this layer slash filter seems to pick out more sort of curved points. And these will work on every number. This is how they manifest with a 5. So if I were to run a 7 through here, for example, I wouldn't see points here and here. I'd probably see a point up here, right, where the 7 suddenly changed directions. And then for this one, that seems sort of more activated by curves. If I had something like a 7 that had a really straight line, it probably wouldn't pick up anything there. So this is what image processing and OCR rely on, are these convolutional neural networks that basically select out individual features. Here's an even more complicated example. Those are layers that were developed for the MNIST database. They're very specific to the shape of numbers, right? Because the neural network responds to what its inputs are. This is trained on a series of 10,000 photos. These are your second layer, and these are your third layer. And you can see you get different emphases, right? So in our second layer, we see sort of geometric emphases, circles, crescents. And then over here, we also see color-based emphases because we trained it on color, right? So what you can get, there's no intrinsic technical limitation. What you can get is really just premised on what you started with. So if you started with a color-driven problem, right, and you had different channels for different colors, you will get filters that look at colors. On the other hand, if you start with a relatively simple, not saying this is simple, right, because it's kept people busy for decades, but if you start with a relatively simple input, you will get more simple layers. So that, just as a reminder, this is where we are. This is how we're processing, again, just as a reminder, just individual numbers. So that's sort of the starting point to do OCR, right? But this is just 10 digits, 0, 1, 2, up to 9, right? And it's still sort of by a limited number of people. And also, the other thing I'll point out that makes this easy is the numbers are all sort of in the box. You're never going to have something where there's no number in the box or where only part of the 5 is in the box, but you're still supposed to figure out it's a 5. There's nothing like this. So that's still a relatively simple problem. OCR is quite a bit more difficult, as we talked about, because you still need to identify where your text is, what its orientation is, and you also have no idea of what sorts of things are going to appear, right? It's not 0 through 9. It could, even if you're limiting it to English, right, you've still got the entire Roman alphabet and all sorts of combinations of punctuation, et cetera. So I think Tesseract is a pretty well-known OCR framework. I think it remains still sort of the best thing that's open source where you can really see what's going on. I'm not saying it's the best out there. It certainly isn't. But as far as being able to take it apart and know the nuts and bolts, this is Tesseract. So this is actually some of the samples of what they tested Tesseract on. This is back in, I think 2005, something like that. Like really early on, this thing was already not in its present form, but in an initial form developed. And so you can see even here how much harder this is than the MNIST example, right? And why people would never look at this and think, oh, maybe I'll just get some grad students to code up some vectors. We'll just sort of pick out some pixels, right? Pixel position is meaningless here, right? Lower left-hand corner, with MNIST, that might possibly mean something. With this sort of work, it certainly doesn't, right? We can have text that overruns like it does here. We can have text that goes right up to the edges. We can have text that is incomplete like Chicago, and we're still supposed to know that's Chicago, right? But you really need to be intelligent to know what that is and have a lot of context that we can't expect a machine to have. So this ends up being, you know, I showed you this model, and in a way this looks really complicated. But in a way, it's also really easy because it's a couple of matrix operations. And if I know that, I can actually summarize the entire model with just, you know, pointwise matrix multiplication and classic matrix multiplication, and I'm done. I can write this in a couple of lines of code. It wouldn't be good code, but I could do it, right? On the other hand, Tesseract, because it's solving a much harder problem, is much more complicated and has many steps, right? So it does things like connected component analysis to try to identify different segments of your image. It then makes blobs of text and tries to break them down into lines of text. Why is this hard? Why is it hard to identify lines? Well, your image might be skewed, right? It might be sort of slanted, or maybe it's sort of got folded up in the scanner, so it sort of goes up and then it goes down and all sorts of things like this. Then, after they do that, identifying where the words are, then they identify individual words, and they do this in 3 passes. So in the first pass, they just do their best. They mark places that are fuzzy. In the second pass, they also have been training their classifier as they go. So as they're identifying letters, the classifier sort of learns, just like a human. It's getting better and better as you go through the document. So then they think, oh, we learned so much from this document, let's go back to the beginning and do it again. So they do a second pass, where now that they're better, maybe they can do a better job on the earlier work that they classified. It sounds a lot like just how we work, right? We work through a problem set. Oh, now that I figured out some stuff, let me go back to problem 1 and check that again. Same idea. And then finally, on the third pass, this is sort of where they deal with the stuff that they still have no idea. Take their best guess, move on. Even more nitty-gritty, right? So line finding, how does line finding work? They actually fit lines, a couple of splines to the line, and sort of try to figure out the geometry of the line. Then they chop up words and try to delineate individual characters, because this is really one character at a time recognition. This is not figuring out the whole word. It's like, what is this letter? What is this letter? It's not always easy, especially with this training data they got, right? That newspaper font. So they also have to figure out sometimes how to chop up different letters, right? So if letters are connected, exactly where do you chop them? And where you decide to chop them might impact how good a job you can do on guessing what they are. So you have all these sort of related problems that feed back and forth, back and forth. Interestingly, as far as I know, they don't do linguistic analysis, so they don't sort of go back and say, now that we sort of have this in computer English versus an image, does it make sense what we wrote? That would be a whole other problem, which we're certainly capable of solving, but it's a separate one. They do get the job done, though, right? So we see the error rates for text are something like 1 or 2, occasionally 3%. Pretty good. But it's a much more complicated model versus the convolutional neural network, which I can sort of easily describe. So that's sort of the optical character recognition. It remains a harder problem than image segmentation, but it benefits from the advances, right? And this is what you often see as different problems feed off of each other, and people can sort of cleverly see that solving one problem actually gets you a long way to solving another. Okay, so let's talk about text to speech. Obviously, lots of reasons we'd like to be able to do this. This would have been helpful to me, for example, in Japan in 2012 when I wanted to ask people how to get somewhere if I could have just typed it in some pre-canned Japanese and at least read it out to them or showed it to them or whatever. But there are also, again, interesting connections. So for example, what people have found is if you can do text-to-speech well, those same models can usually do pretty good music generation. It's the same idea of you're taking a digital format and turning it into some kind of analog representation, and one where we have an idea of what should be natural. Similarly, any translation, as I was saying, from digital to analog, this is the sort of model you're going to use. And finally, an interesting one, this is pretty recent that people are doing this, completing missing parts of images, right? So maybe you did a pano, and you have a black spot on the top, and your brain can complete it, right? You sort of know there should be some tree cover there, or there should be a blue sky or something like that. The sort of model that does text-to-speech is the same model that can sort of fill in those black spots in your image and make them look much more natural. Okay, so I'm not going to do the whys anymore. I think we sort of know why these things are useful. Let's just talk about how these work. Up until recently, and really in industry uses, even now, still, what people do is they use a large database of pre-recorded speech. That's how people do text-to-speech. You can do it at the level of individual units, right? So if you're a linguist, you can sort of say, oh, there's a vowel, or there's a diphthong, or there's a very common consonant-vowel pair, and arrange recordings of all of these things. You can do them at different levels, right? So like individual sounds, or like 2 syllables together with different stresses. You can do whole words or phrases. So linguists and sort of AV type people have always been very involved in this. This is really more of an art than a science, to the extent that you want to sort of naturally take things recorded separately and put them together. I think we all know this doesn't really flow like natural speech, right? Because every language has sort of different inflection points, different tones rising or falling depending on exactly what you're saying. You can't capture all that with a database. But when you do it this way, you have more of a database find and retrieve mission. This is not really a CoreML style of application, and it's very storage intensive. Also, it often sounds very unnatural, right? And I think maybe we get more and more used to this the more we hear, but it's never going to be great. Here's a model that solves this in an entirely different way. This model just says, give us the text, and we're going to turn it into speech. And of course, they started with training data. So to train their model, of course, they had to have text and recordings of speech. It's a very intensive process. This is not easy. It's expensive and time-consuming. But what they figured out once they had this really great data set was this shape of model did a really good job at producing very natural-sounding human voices. So let me explain how this works. Here's the input. So the input is basically an audio waveform over time. So they take a slice, maybe 10 milliseconds or 10 seconds, whatever it is, depending on the range. They line up the inputs here. It's like an image, right? So instead of thinking about it like a time series, they think of it sort of as an image, like a waveform. The waveform is loaded here, and they have a number of hidden layers. Remember, layers are just matrix operations. They run it through these matrix operations, but what they do is somewhat different from the CNN we talked about. So with the CNN we talked about, you have sort of these filters. You run them across the whole thing evenly. Interestingly there, you treat the whole image equally. All parts are treated the same. All parts have the same image, right? And that makes sense because for an image or for character recognition, all parts are equally important, right? I mean, which part is the most important part of the 5? Well, they're all important, right? And where they are doesn't matter as far as their importance. Not so with speech, right? So when I'm talking, what's the most important thing I said? What's the most important? I kind of gave it away. It's the thing I just said, right? Just sort of like when you're thinking about what someone's going to say next, you think about what they just said, not what they said 5 minutes ago. So you want to prioritize the things that were just spoken, but you also want to have some memory. And that's what this model does. This is the oldest, and this is the newest data you have in this audio waveform. And so what they figured out is you take something that's a little bit like the CNN we talked about, but actually it does a couple things. It skips points so that it can go further back in time. So the first thing they found out is you don't need to have every point. You can skip some points. And the second thing they found out is they have this directionality. So the most recent input goes in and is stronger versus the most distant input might only make it in once, like this. So you have these filters, like these filters get applied to everything, and then certain filters only get applied to the recent, and the really old things only make it in for a couple. So that's the architecture. What did they find? Well, firstly, they did quite a bit better than the other models that are out there, like concatenative, which is when you just record speech, or parametric, when you sort of try to come up with one way of making speech with just a couple of variables. They beat both of those hands down, both in English and in Mandarin. So it's also unusual for the same model to do well on more than one kind of language. And they came pretty darn close to actual human speech as rated by human raters. So they played these phrases for people, and you sort of rated them on how natural and how intelligible they were. And they're doing almost as well. So that's pretty amazing with this really simple architecture, right? And I mean, this architecture wasn't easy to find. Easy to understand, not so easy to find. So also keep that in mind. There are plenty of architectures people find that don't really work. But they found here one that with the sort of modification to how we process images, right, of prioritizing recent rather than prioritizing everything, they could take something that works for image classification and make it work to produce voices. The other really cool thing they did that hasn't been done before is they added some inputs so that you could say what individual was speaking. So I believe they had 12 individuals in the original data set. They had a variable that was basically just the speaker's name. They found that they didn't just produce one voice, they produced one voice per speaker. And so they were also able to sort of customize, right? So if I want my GPS to use my mom's voice, but my friend wants my GPS to use her boyfriend's voice, like we can both have our way if we have that data set. So that's also really interesting and cool, and shows this sort of unexpected connection between image generation or image classification versus voice generation. Okay. Speech to text, the opposite problem. how do we think about this? Well, one thing I want to point out is just like text-to-speech has many connections to music, it's the same for speech-to-text, right? Music classification, recording, any sort of AI you'd want to do, listening to music and making a decision about it, is very similar to speech. And in fact, your inputs are almost always the same for your models. So how do you think about speech to text? Well, the first thing, those of you who have a technical background might remember your good old Fourier transforms, where you want to convert things that you see in the time domain waveforms, and you want to think about them in the frequency domain. For those of you who haven't seen this before, it's really very simple. So let's say this is your original data, this red line I have. This is your time-based data. What you probably notice is this looks like sort of a couple of different things going on, right? There's sort of this slower wave that has these big undulations, but then there seems to be this sort of faster thing going on. So what we can actually do is decompose these. We can say this red curve, if you look at it carefully, is really just a sum of like a slower curve, a medium curve, and a fast sine curve. And so what you can do is you can project this thing into the frequency domain and see which frequencies are really popular versus which ones are just noise. So people will take speech or music inputs, they will do this, and they will get images like this one, right? So now we have a spectrogram of the word hello. This is somebody saying hello. But we're thinking about it, this is as time is passing. This is the frequency, right? So now, instead of each point in time being recorded as a slice here, it's recorded as a slice here. So over time, this is what the word hello looks like. Now, what's great about this is I've turned it into a problem that I know how to solve, which is image processing. It's also, though, giving me more data in a way, right? Because if I start here, I might think I only have one variable, right? I have sort of time versus whatever the height of this red curve is. I have now converted this into something that has a very rich set of inputs, also very helpful for me. The more inputs I have, the more different features my model can notice. So in this particular case, the people who built this speech to text actually then used this to build what's called a recurrent neural network. It's the other main kind of neural network to figure out what people were saying. And the way they did that was they took each slice here. This looks like an image. It looks really complicated. It's actually just a matrix. It's not even a matrix. It's really just a list, right? A one-dimensional list. For each frequency, what was its intensity? We run this through a recurrent neural network, which I am about to explain. There is no reason you should know yet what it is. This thing, what it spits out for you, though, is, say, your likelihood that you're saying ah versus buh versus sa, and so on. And so from this, you begin to build up a model of what people are saying. You can do it either syllable by syllable or word by word. How you're doing it just depends, again, on what you're giving your model to train on. Are you giving it individual syllabic breakdowns because you have a linguist who can help you do that? Or are you just giving it the full word and saying, figure out if this is hello or something else? So recurrent neural networks, you definitely want to know these. These are sort of the wave of the future. So convolutional neural networks we talked about, those are the ones they pass the filter around. They sort of create those beautiful features, and that somehow spits out a number or a word. These, interestingly, are more simple in terms of their parameters, but they're very weird. You take basically the exact same matrix multiplication, and you do them again and again and again as you sort of input more data, and your cell evolves. So what this is what it's depicted as. It's actually rolled out like this. So this is like time step 1, time step 2, time step 3, and so on. And so going back here, and actually all the way back here, this is really time step 1, and time step 2, and time step 3, and time step 4. So at each time step, I'm feeding in a new array of values. It's chugging through some matrix multiplication, updating what's called a hidden state, outputting some stuff, and then saying, OK, give me your next step. I give it the next step and the next step, and it goes. That's when it infers. Training these things is really complicated, and that's why they remain a little less successful than the convolutional neural networks. But the problems they can solve, like with language, music, translation, prediction about the time, are also really important problems. So we're certainly going to see more of these in the future. So these are the matrix multiplications here. I'm not going to go through this in much detail. You should just think of this as I update a matrix and multiply it by another one. I update a matrix and multiply it by another one. And that's really all it is. It's some linear algebra. It's much harder to think about than to just chug through it mechanically, which is weird because most things it's the opposite, right? You can sort of think about them, but when it comes to implementing them, it's like, whoa, really tough. Okay, and then just one final note on image identification. You've already heard me talk about this a lot because it's so fundamental to other technologies. Everything relies on these convolutional neural networks. But so just to point out, if you can identify what an image is, you can probably localize the object you're looking for inside your image. So if I show you a picture and say, is this cake? If your algorithm can say yes, then probably with a little bit of training, it can also sort of draw me an outline around the cake. OCR we already talked about, right? Totally the same problem, although OCR is even more difficult. And facial recognition, same technologies, right? If I can sort of identify where the face is, where the eyebrows are, et cetera, I'm well on my way to facial recognition. Object localization, just to show you state of the art, and this is like just a random blog post, this is not a research paper. You can easily tell your algorithm, show me where the man is, show me where the chair is, show me where the cow is, and what I think is really cool, this chair, like my brain puts it there, your brains probably put it there too, but actually you can't really see it, right? And yet it still knows the chair's there. There's sort of slight variations in the pixels, plus it's also intelligent just like we are, so it can pick it out. So how do you do this? Just very, very briefly, and I'm happy to talk to people after and send out my slides for people who want to know more. This is this very clever thing where you take a convolution. We talked about this already. A convolution is sort of taking an image, collapsing, collapsing, collapsing. But now what we do is we get to the end of the collapse, and then we blow it back up. We do the opposite. We do a deconvolution. We use filters to make images larger rather than making them smaller. And so what happens is you run this thing through. First you convolve it, and then you deconvolve it, and this is what pops out. And I mean, I just think that's amazing. All you need to do is set up the matrix multiplication and then have hours and hours and weeks to train these things. The training is the really tough part. This is sort of the nice thing at the end of the training. But this is just to tell you this is how you can do, and this is the technology you would use, right? So it's nothing that you can't sort of understand after reading a paragraph. It's a couple of matrix operations. Okay, so I don't have too much time. I want to just briefly talk about sentiment classification. I apologize for going a little fast here. I just want to point out sentiment classification, if things are happy or sad, is very much related to translation, right? English to German, German to Mandarin, you pick it. It's related to text generation. So if you want to have your computer write stories for you or also write music for you, it's actually a very related problem. And of course, something like the Holy Grail, you'd love to have a chatbot that can pass the Turing test, right? If that happens, this is sort of some of the technology that's going to be related to that most likely. Okay, so traditional NLP tended to rely on sort of statistical methods, Bayesian methods, right? You had these sort of bags of words. You had a bag of words, and it tended to have a positive rating. Oh, so some of those words must be positive. You had another bag of words. Some of them were negative. OK, I'm going to guess some of these words are negative. You just sort of lexically looked at things. Oh, it seems like the word sour is a bad word. So you kept a dictionary. Sour is a bad word. Or like sweet. Oh, that seems to be correlated with people being happy. I'm going to give that sort of a positive rating. Recently, with deep learning, people are moving to things that sort of, instead of just sort of putting labels on words as far as probabilities, are sort of trying to understand what's going on. And not in some deep philosophical way, but understand how words are related to each other. The way this is done is something called word embeddings, where every single word is turned into a vector. And not like one vector per word. It's not like A is 1 and the is 2 and so on. It's like you might have a vector with 20 dimensions, and the could be like 0.1, 0.3 minus, it's like a vector projection. This is sort of what this would look like and how this originally happened. People said, oh, we have all this language on Wiki. What we're going to do is we're going to write a model where we randomly assign, like we take every word and we give it a random vector, just to start. Like this word the randomly has this vector, and the word man randomly has this vector, and the word woman randomly has this vector. We're going to run it through some kind of complicated model where first we condense it and then we blow it up, just like we talked about with the image segmentation, right? You take something complicated, you project it down to a simpler space, then you project it back up. In this case, what they did is they just try to recreate. So they take the words, the vectors that have been randomly assigned, they condense it down, they blow it back up, and so they just try to take wiki and translate it back to itself. And magically, when you do this, you end up getting what are meaningful matchings of those vectors to the words. So you allow the vectors for each word to evolve. You end up getting vectors that are meaningful. Like the fact that man has like a 1 in its first feature might match that woman has a 1 in the first feature because they're both humans, something like this. This has been amazing. So just something like this, right? Like you literally have a table for each word with a couple of values. And that's your word all of a sudden, right? We think of words as words. Our computers see them as vectors. If you plot these vectors, they're actually meaningful. So here's an example of plotting the vectors both for English and for Chinese, and actually they match. And you can see a lot of these for different languages. If you sort of do Chinese wiki and English wiki and then plot the words after, the words that you plot will be close together. And so this is a way that people are beginning to do translation, right? How does machine translation work? Nobody knows exactly what state of the industry is, but most likely it's using something like this. One more thing I'll point out is this has also been a way to find out that language is kind of sexist, right? So when you sort of plot words like woman and nurse and babysitter, those go together, but somehow surgeon is sort of projected into another space, you know? And so we have this geometric way of discovering either sexism or racism in our language. And so that's also become a really useful tool for researchers. I see I'm over time, so I'm just going to very briefly talk about what's likely to happen in the near future. So far, deep learning is not very good at predicting the future, right? Neither are humans. So what we've seen so far is deep learning is good at doing what humans are good at. That's great. If we can have an app that's like a mini human, that's wonderful. If it could be even better than a human, though, that would be even better. So people want to do things like stock market predictions, weather predictions, traffic predictions. That would be wonderful. People also want to take these existing open source models and make them even easier to train. So right now, if you get an open source model and train it, you still have to do a lot of work. Like you still, if you want to have a unique application, you download something from the internet, it's not going to work that well on your app, right? Like if you want to just identify buildings in Northern Virginia, you probably want to train that a little bit more in your Northern Virginia context. I especially think this year's holy grail is like these realistic chatbots. People are getting pretty good, so that's also a very active area of research. Obviously, tremendous economic opportunities and also computer science advances that you're going to make if you can solve this problem. And finally, distributed training and inference. So people really are trying to figure out a way to train models on apps. It's not going to be easy, but I'm sure they're eventually going to get there. So eventually, not only will you have to load the black box models, but you're going to have to start training them. So I think that's the future for iOS. So thank you.